Cheap electricity is getting easier to generate, yet dependable power is getting harder to buy. That sounds backward, but it is the core shift now hitting grids, industry, and compute. The reason is not politics or market design, though those matter. The deeper reason is thermodynamics. Every energy system bleeds some value as waste, because entropy always increases. You can harvest sunlight, burn fuels, split molecules, or move heat around. You still pay irreducible losses when you turn that into useful work at a specific place and time. So the new bottleneck is not energy in the abstract. The bottleneck is delivered controllable exergy. Exergy is the portion of energy that can actually do work. It depends on quality, not just quantity. A kilowatt-hour at noon in the wrong location is not equal to a kilowatt-hour at 7 p.m. A megawatt of low-grade heat is not interchangeable with a megawatt of high-temperature process heat. Even perfectly clean power can be operationally scarce if it arrives with the wrong timing, grade, or reliability. That framing changes how to read cost curves. Nameplate generation cost can keep falling, especially for variable renewables. Yet the expensive layer migrates downstream into firming, storage, transmission, interconnection, and power electronics. Reliability services start to dominate. Frequency control, reactive power, reserve margins, black start capability, and congestion management become the real price setters. You can see it in interconnection queues and in the growing value of grid capacity itself. The system is no longer paying mainly for making electrons. It is paying for making them show up on demand in the right form without destabilizing everything else. A useful mental model is to separate cheap energy from cheap power. Energy is the total over time. Power is the rate, the ability to deliver now. Variable generation can be cheap on average and still fail the power test. If demand peaks after sunset, surplus solar at midday does not solve the problem by itself. Turning surplus into firm supply forces you through conversion steps, and every step throws off heat and loses exergy. That loss is not a rounding error. It becomes the business model. Now consider solar, because it is the iconic learning curve technology. Photovoltaics will keep improving. Materials engineering, better contacts, tandem stacks, and clever carrier selective layers can push performance upward. Fielded systems can also get cheaper through manufacturing and deployment scale. But the efficiency trajectory is bounded. Detailed balance limits, recombination losses, spectral mismatch, and heat rejection are always there. Progress moves you closer to the ceiling. Progress does not remove the ceiling. That matters for strategy because many plans quietly assume open-ended improvement, where iteration can keep compounding with no physical endpoint. Solar is physics. You can refine architectures, reduce parasitics, and improve extraction. At the end, you still have to reject heat, and you still have finite gradients. Those are not negotiable. So when someone sells nearly free power forever, ask what they mean by delivered, firm, controllable service, not just panel cost. Storage is where confusion gets even more expensive. People often say, we'll just store it, as if storage is one thing. Storage is many thermodynamic niches. Second-scale stability is different from multi-hour shifting. Seasonal balancing is different again. Thermal storage, sorption systems, phase change materials, and thermochemical loops all depend on temperature windows and material cycling stability. They also depend on heat transfer rates, which limits power density. Most importantly, stored energy is not automatically dispatchable work. You have to specify the grade and the recoverability. Heat illustrates this cleanly. Low-temperature heat can be abundant and still be hard to use. If you need a temperature lift, you are forcing heat to flow uphill, and you pay for that with additional work and additional losses. Even very good thermal storage can deliver the wrong kind of heat for the job. That is why district heat and cooling networks are quietly becoming strategic again. They can reduce total entropy generation by matching sources and sinks locally. Waste heat only becomes an asset when the integration is real, not just a slide. Industrial processes bring the same point into sharper focus. Much of heavy industry is not constrained by electricity supply alone. It is constrained by high-temperature heat, by chemical potential, and by separations. Separations, purification, and phase change steps have minimum energy requirements. Melt crystallization, desalination, refining, fertilizer, semiconductor manufacturing, many of these processes face irreducible work costs. Cheap electricity may lower operating cost, but it does not make the thermodynamic floor vanish. If your plan assumes it does, the plan is wrong. So industrial electrification is not a single pathway. Some processes should electrify directly because it removes conversion steps. Others may need chemical carriers like hydrogen, or synthetic fuels, or nuclear heat, or redesigned process chemistry. The right answer depends on an exergy audit, process by process. Without that, you risk building long conversion chains that look clean on paper, yet leak value at every interface. Now add computation, because it is becoming an energy story, not just a technology story. Large-scale AI, inference factories, and dense data centers are not only big electrical loads, they are thermodynamic systems that must reject heat continuously while meeting tight uptime and power quality requirements. A data center does not just want cheap average electricity, it wants stable voltage, low disturbance, and high availability. The moment you require that, you are back in the world of firm capacity, grid services, backup logistics, and cooling constraints. Heat rejection can become a site-level limiter, even when upstream generation looks abundant. Ambient temperature, water availability, and thermal pollution rules matter. So does the ability to use waste heat, which depends on nearby demand at the right temperature. That makes siting a first-order strategic decision. In the near term, it can matter as much as the power purchase agreement price. Across all these domains, the same planning error repeats. Leaders optimize for the wrong unit. They optimize for raw kilowatt-hours or for levelized cost at the generator busbar. Yet what society and firms actually buy is a service: light, motion, computation, purification, cooling, and high-temperature process heat. Each service requires a particular exergy quality delivered at a particular time and place, at a particular reliability level. When those requirements are ignored, cheap generation does not translate into cheap outcomes. A practical consequence is how to rank projects. You want portfolios that maximize delivered, controllable exergy per lifecycle dollar, not nameplate capacity. Any investment memo that omits storage losses, conversion losses, curtailment risk, interconnection delays, and grid upgrade needs is incomplete. The same goes for contracts. If procurement buys undifferentiated energy, then someone else is implicitly carrying the risk of delivery, firming, and losses. Eventually, that risk shows up as price shocks or reliability failures. The policy implication is similar. Energy plans that report annual energy totals can hide adequacy risk. Hospitals, water systems, public safety networks, and industrial facilities do not run on annual averages. They run on worst-case hours. They run through storms, heat waves, fuel disruptions, and cyber events. When reliability is treated as an externality, the system will underinvest in the very layer that makes energy usable. Looking further out, the limits do not fade. Even with advanced generation, even with orbital collection or exotic concepts, you still face entropy, waste heat, and finite gradients. At larger scales, heat rejection and governance can dominate. Post-scarcity becomes less a physics claim and more an allocation and coordination claim. Power can be abundant and still not be cheap once you price controllability, delivery, and stability. So here is the takeaway to carry into every strategy meeting. Stop asking whether energy will be cheap, and start asking whether delivered, controllable exergy will be abundant where you operate. The winners will be the ones who invest in the bottlenecks,